Hello.
Hello.
Yeah, you can begin.
Uh, Hello everyone. Welcome to the presentation. The topic structure for motion. We'll discuss about the theory and its application.
So there is you're not properly audible.
Am I audible now?
Actually,
Hello.
maybe ask if somebody else gives the feedback, that would be better.
Yeah, your
Uh,
voice is pretty unclear.
Sumit?
A bit unclear.
Just a moment. Now it's clear.
Maybe
Hello.
you can pull the mic towards you or something.
Hello. Now it's fine.
Yeah.
Yeah.
Yeah, better than before. Yes.
Okay. So what is the problem? Like what is structure for motion? So so we have some camera points, like camera in a motion, which captures the scene, like a scene or buildings or any scenery. So there are two things we want to estimate from. Like we don't know the where the views were captured. We just have the images with us. So we need to construct the scene geometry from there, and also we want to estimate the camera motion. Like where were the camera like when it was taken the shot. So we want to estimate the camera coordinates. We also want to estimate the scene geometry. So these are the two problems we will be solving for structure of motion. So before diving back into structure for motion, let's understand the simple studio. Okay, so first we'll discuss the steps involved. What is the pipeline for structure for motion? So the pipeline involves, first we do some feature matching, like we find the corresponding points between two images. So the common points between the same points of interest in the two images, and we know that if there are 2 points, there must be like some points would be not one to one correspondence, like there would be error in those points. So we need to reject those points also. We will do outlier rejection. So the algorithm we will use will be ransacked. The second part would be the estimating the fundamental matrix. So afterwards we will be doing estimating the essential matrix from the fundamental matrix, and then we will be estimating camera poses using the essential matrix. So in the camera, when we estimate the camera poses, there would be a problem of chirality. Like there would be four different configuration of rotation and translation. We'll discuss later. So we need to check which camera poses are accurate. So we'll do using triangulation. And the last thing we'll be doing is bundle like this. So this is the pipeline of structure for motion. So before diving, we'll see how the simple studio works. Like you can see here, if you have there are two cameras, left camera and right camera. We know all the intrinsic parameters of the camera, and the camera is displayed by horizontal frequency. So if we take any point in 3D workspace, so we can using a simple geometry, we can know the equations, like what would be the image coordinates in the left camera and what would be the image coordinates in the right camera. So as we know, there was the second camera is displayed, the left right camera is displayed by B in the x direction only. So it would be x minus. This would be the only difference in the two equations. And using this, we can easily estimate x, y. So we'll easily know the 3D world coordinates using just a simple binocular stereo vision. So this is the basic stereo used for like estimating the depth, disparity or depth. So now the question is, how do you estimate the 3D structure from different two arbitrary views? Like you don't know the beforehand you were knowing the baseline that the first camera is displayed by distance d in the x direction. Now you don't know that. So how do you estimate 3D structure from two arbitrary? So what are the steps involved in that? So first we'll assume that we know the camera metrics, like intrinsic parameters of the camera for each camera, like left camera and the right camera. So we'll find the corresponding points of interest between two images, and using that we'll be estimating the translation and rotation of the right camera with respect to the left camera. So this is our goal to estimate this. So how we'll go along, we'll discuss later. So this is a simple epipolar geometry. These are epipoles, left epipole and right epipole. So this is a like seal structure. And okay. So we know the epipolar constraint. We have studied in the class, like the coordinates on the left image into the essential matrix in the right coordinates is equal to 0. So we can rewrite this in the image coordinate form, considering the fundamental physics. And you know the image coordinates. So this image coordinates we can get from corresponding points matching, like feature matching with the two images. We can estimate the common features between the two images, and you can have this UL, UVL, UR, VR like pairwise coordinates available to us for an image, and using that we can estimate the fundamental. So the same thing we did in homography earlier, we'll be doing here. Like we'll be rewriting this equation, and we know that this particular nine dimensional vector is unknown to us, and A is known to us because we have ULVR, URVR, URVR, ULVR coordinates for each. So the next question arises: how many points do you need to estimate F matrix? So in homography, there each point corresponding to two constraints. So there we required only 4 points. So here we require, since the points correspond to only one constraint, we require a minimum of 8 points to solve this equation. Therefore, it is called 8-point algorithm. So we can estimate F using this. So the next question arises: how do you estimate the correspondence, like the point correspondence is feature matching between the two images? So finding the feature matching, we can do by epipolar line. We know the geometry. We have estimated the F matrix, right? So what we can do is, you know the ULVL. You could select a point of interest in ULVL. You can use any corner detection algorithm or edge detection algorithm to have your interest point, the left image, and you will get the equation of a line in the image coordinate for the right image. So using that, you can estimate you have a 1D line the right image coordinate frame, and we can do 1D search. Like we know the template in the left image, we just use some SSD or some measure to do the template matching on that particular line. So it reduces to 1D search. So we can find corresponding points using epipolar line geometry. Or there is one more method, you can use SIFT also to do the feature matching to find the point of interest corresponding between the two. So now the natural problem arises with the feature matching. So there are some outliers, like some points will be matched properly, some points would be not matched properly. So how do you avoid this outlier? So as we discussed earlier, there is an algorithm called Randstad. So what it does is, I will explain in plain this example, line example. We know that there is a linear line. So this is the main line of interest we want to have. So what we do is we take any 2 points and estimate, like we start making, we have the 2 points, so we can make a straight line out of it. And what we do is we try to bound an error boundary in the line. So this is the error bound, and we calculate how many points lie in this error bound. So we do this iteration one more time. We change the random point. We take any other 2 random points, like this. We have taken this 2, and we calculate the points lying in those error bound. The same we do it here, and afterwards there would be one iteration where the points would be maxed. So that would be our final, like this would be the straight line we want. So we take the maximum. We take a iteration number. How many iterations will we do? And if in any iteration there is a maximum number of inlier points there, so we'll take that particular iteration as the final iteration, and the line corresponding to it would be our goal. So we can use the same thing here. We can choose 8 corresponding points between the 2 images. M is the number of iterations. This is a pseudo algorithm for doing Randstad. So you go from M1 to M iterations. You choose a corresponding 8 points between the 2 images. You estimate the fundamental matrix. And afterwards, what you do is, earlier we were using the straight line as our criterion. So what we do here is, we take our consideration of image coordinates into fundamental matrix, into the left into fundamental matrix into right image coordinate should be equal to 0. So we bound with an error here out of this. So how many points lie in this satisfies this? If more points are satisfying this, we do the iteration and we take the iteration which has maximum number of points. So that way we can get can reject the outliers, like we are rejecting this point in fundamental matrix calculation, and we are taking points which are very like strong, like they have proper correspondence between them. So that way we can reduce the outlier. So this is one of the algorithms. So now we have estimated the fundamental matrix. So how do we estimate the essential matrix? So essential matrix is simply intrinsic matrix of left camera into fundamental matrix, transpose of that fundamental matrix into intrinsic matrix like of right camera. So you know the essential matrix direct from the calculation, because we have taken assumption that you know the intrinsic parameters of the camera while taking the images. So after that you have estimated the essential matrix. So you need to decompose this essential matrix into rotation and translation. So you can use SVD to do this. So the two solutions we get after decomposition is T and R. Like this is the translation matrix, rotation matrix. So you notice here there is plus minus 1. So there are approximately 4 combinations possible. So there are 4 different camera poses that can be possible from the essential matrix decomposition. So how do you estimate which camera pose are right and which camera pose are wrong? So we use a simple method. We know that the point of interest should be in the front of camera. So we have the 4 different geometries here, as you can see. The A shifted there to the right side due to plus minus right on a B is 180 degrees flipped here. So there are 4 different configuration here, and we know that this is the only configuration which is right. So how do you estimate it? You can by triangulation you can calculate the 3D point here and see what's the Z value of that 3D point is. What is the sign of the depth value, like Z for the camera coordinate with respect to camera coordinate. If it's positive, then it is the right camera pose. So we do this for all the points of interest, and we take a camera pose which has maximum number of points satisfy that kinetic condition. So how do you do this triangulation? We have estimated P. We have also estimated P dash. We know the R and T, so we know the P dash also. So we have both equation with us, and you need to estimate X. So we have the point of interest X and X dash in the right and left image. So as we are doing in fundamental matrix calculation and homography, we restructure this equations to AX equals to 0, and our A corresponds with this matrices, and you solve using SVD and get the X factor out of it. And using that, after we got the X factor, we can, using a kinetic condition, we know whether what camera position that is. So this is one of the solution for this. So after we have calculated all the camera poses and 3D points. Now we want to refine it. Like we know these are not correct because there would be some mismatch and everything possible while estimating. So there is a algorithm bundle like this. It's a non-linear algorithm. So what it does is, you know the X of interest, you know the camera poses also. What you do is you simply take a projection of this point, whatever you have calculated over 3D coordinates, onto the image plane, and you calculate the difference on the image plane. What is the difference of that point with the projected point, and actual point, you know the correspondence point. So you take the square differences. You take for every pair of images possible, wherever there is, and there is a visibility matrix multiplied by V. So if there are 2 views in which some correspondence points are there and some 2 views there won't be a correspondence point. So using the visibility matrix, we ensure that those points are only taken into consideration for reposition error. So this is, and then we do the nonlinear refinement, like we change poses and coordinate system to adopt to local minimum of this reprojection. So this is the final bundle. So this is the pipeline for structure formation from start to. So now Sumeet will discuss an application of structure formation. Sumit.
Yeah. Hi everyone. So I'm going to explain a paper titled "Applications of CNN for Low Vegetation Filtering from Data Acquired by UAVs." So this is not properly structure of motion. This comes under the domain of photogrammetry, but here structure for motion is used. We will see that in a bit. And yeah, next slide. Yeah. So UAVs are unmanned aerial vehicles, which we usually call drones. And it is a low cost way of collecting data using photogrammetry on images of relatively smaller areas. The advantage of using UAVs is high operational flexibility, high spatial and temporal resolution. So what the authors have did is they have developed an algorithm to filter out points that indicate areas covered in low vegetation from the generated point cloud. Okay, so this paper presents a 3-layer filtering algorithm based on CNNs, and the solutions provided here reduce the error in the digital elevation model points by around 60 to 70%. Next. So what is a digital elevation model? So a DEM is a representation of a bare ground topographic surface of the earth, which excludes trees, buildings, and any other objects or surface objects, right? So in the image, you can see on the left side, we have a photographic aerial view of a place. And on the right side, we have a digital elevation model where we only have the uh, elevations as encoded by different colors. Next. So now onto the methodology. So the dataset acquired are at two different locations in the south of Poland. One is from the village of Laziska, which is used to train and validate the network. Another is from the village of Jerzmanovice, which is used for testing. Okay, so the measurements included in a UAV dataset and reference measurement for the height of points located on the ground. So the reference measurements were done manually using a total station. Okay, and during the measurements, the objects were divided into regions with same type of condition and plant coverage. So low grass areas could be one of the same type of region, and high grass areas, meadows and road areas, and so on. So while clicking the pictures from the drone, the side and forward overlaps were designed to be at least 50 and 70%. So while moving forward, there would be at least 50% overlap between two consecutive images and at least 70% overlap for forward overlap. Next. Yeah, so this is what the sample image looks like. We have a black and white image, and the division of dataset is done as parts A and B, where A is the low grass or mode area, and B is the high grass area, which is grass about 60 centimeter tall. And you can see in the photo, we have train and validation data. So train is used for training, while validation was used for training validation. Next. And again, here is another kind of data. This is from the Jerzmanovice village dataset. Here you can see a bit more of the classifications. A1 is mowed grass, A2 is paved road, and so on. Okay. Next. So data processing. So data processing was done in 3 steps. First was the classification of point cloud into high grass or low grass classes. The second was the classification of point cloud fragments that represented the high class for points reflecting in ground class and remaining points. So here, just sorry. So all the points which were not in high grass or ground class, they were eliminated. And next was the corrections of heights of points, which were classified both as high grass and ground class. But this was a optional step. Next. So preparation of input data. So the input data was presented as a fragment of grayscale images with an 8-bit depth. So a 65 by 65 grayscale image was input to the CNN, and the entire point cloud was divided into adjacent cells. And in each cell, the point with the lowest height was selected and attributed as the height of the cell, while the remaining points were discarded. And the cell values were transcribed into a matrix labeled R. The missing values of R were filled by the nearest neighbor interpolation method, and a Gaussian filter was applied to the R matrix, and we obtained a G matrix. Next. And also the correlation between the photographs and the actual height of the data was done by SFM algorithm from the Agisoft software. Just a side note. And another thing is, so continuing, an M matrix was created as the difference between R and G. So M matrix elements were processed into a closed interval and saved as an image I, which was then fed to the network. Here you can see the algorithm and the processing steps. Next. So yeah, an illustration. So here you can see the one image, sample image from the Leziska dataset, which is A, and the B and C are the sample inputs which we are provided to the network, which are 65 by 65 grayscale images. Next. So structure of the CNN. So the authors have developed two networks. One is for the classification of vegetation into high grass and low grass classes, and another one we will see later. So here we have first the input layer, which is a 65 by 65 layer, and we have used 10 layers of convolutional layers with 5 by 5 cross 1 convolutions and 1 cross 1 strading with no padding. Next is a ReLU and a max pooling layer, 3 by 3 max pooling layer with 2 cross 2 strides. Another is a fully connected layer, a softmax layer, and a classification output, which classifies the image as high grass or low grass class. And we have used cross entropy loss. Next. Yeah. So another CNN is to classify the points into ground and non-ground classes. The previous one was to classify it into high grass and low grass. This was into classify it into ground and non-ground classes. So similarly, here we have an image input, 20 units of convolution, ReLU max pooling, again convolution, ReLU max pooling, fully connected layer, softmax, and a classification output, which classifies it into ground and non-ground classes. And again, we have used cross entropy loss. Next. So result. So after training, the algorithm correctly classified each image with an accuracy of 99.3. And from the confusion matrix, we can see that the true positive, false positives and false negatives are very low, and it has correctly classified the high grass points as high grass and low grass points as low grass. Next. So this is just an illustration. So the black pixels are the high grass class, and the colored pixels are the low grass areas as classified by the CNN. Next, and contrarily, this one where the black pixels are the roads, pavements, and the low grass areas, whereas the colored ones are the high grass areas. Next. So, in conclusion, we have used CNNs to form correctly a digital elevation model from photographs, and classification of points into ground and on-ground using CNN has given us promising results, but it requires further processing or more extensive data set. But in the classification for low grass and high grass in nearly all cases, uh, the CNN has classified the results correctly. And now Arnab will present the next section.
Hello. Am I audible?
Yes, you're audible. I just wanted to ask Sumit, I missed a couple of points from the last thing.
Yeah, sure.
So
ma'am.
I just wanted to ask if those two data sets were mixed, or I mean, you had different data sets for this, and how many images were used in each case?
So there were around 1500 images, but each one was like fractioned into like smaller parts. So there were around like 100,000 images for each data set, and the other data set, which was the Jerzmanovic data set, it was bigger. So the Laziska data set, it was actually used for training and validation, and the other data set was used specifically for testing only.
Okay, okay. Yeah, please go ahead.
Okay. So this is another application of SFM for scour analysis. So the flow of the water in a river erodes the materials from the river bed banks around structures and transport them to a certain distance until it gets deposited. As a consequence, foundation of a structure is kept in by the erosive force flowing water, resulting formation of scour. And we have to do this scour hole analysis here by SFM. So for the manual data here, they have used traditional instruments like gauges and sensors, and so this will give us the original data points. And in case of scour analysis, the main concern of identification of the maximum scour depth and 3D description of the scour hole due to limited measured data by manual methods, which is by gauges and scour sensor. The data is commonly collected at some selected points. The point data is later used to define the shape of scour hole, either in the form of depth contours or 3D view of scour hole. So this is an experiment to application of automated close range photogrammetry with SFM. So here they used two different pairs, the circular, the usual one, and the hexagonal pairs. Next slide. Okay. So for the method, as I mentioned earlier, they use two different type of pair geometry, one circular and hexagonal. The circular and hexagonal pairs are uh, secured below the sand bed level by 25 centimeter and 15 centimeter respectively, and they have observed that the fully developed flow is attained at approximately 4.7 meter away from the inlet of the flume, as vertical velocity distribution is logarithmic, and the piers is then located at approximately 5.75 meter from inlet. The center is it is called star center, is as taken as 0, 0, for our analysis. Next. Okay, for the procedure, the respective pier model is embedded in the flume, and the sediment bed surface in the flume is leveled to 100 centimeter from the bottom of the reference with the help of a point gauge, the instrument, and the thickness of the lead sediment bed is 25 centimeter in uniform throughout the flume. Uh, the after the experiment run, they control the water depth and the water flow with the tailgate. Is this in procedure? Next, please. Yeah, each experiment ran for 3 hour duration for the scour hole development. And the process was observed to be close to the equilibrium condition. It takes up to 3 hours, and the flow depth is maintained 10 centimeter in all cases, adjusting by it is done by adjusting the tailgate. And after the experiment is done, they allowed to drain off the water from the tailgate. So this there is a thing to note that the runs were shortened because the purpose of the study is only to demonstrate the capability of SFM, not not the scar phenomenon. That's why they shortened the study, the runs. Okay. So next, please. Yeah. So for the data acquisition and ground truth data, the distribution of the grid points in the figure there established based on the dimension of the scar hole. Here uh, the circle and the hexagonal blue area is the scar hole, and the middle in the scar hole the middle is the origin. Okay, the profile of the maximum scar depth is observed at the discrete points along the longitudinal direction marked by the green color line. And these curve depth data collected by the point gauge and gridded points, a set of photos are captured before and after each experiment run using DSLR camera for the purpose of the automated CRP analysis. Okay, next. Okay, so since they capture the photo from above 1.2 meter from the flume surface, so if there is any blurred image, they immediately discard the image from the original photo set. They a total of 25 to 70 images are required for each run. It's also depending on the scar hole size of the scar hole. It is also noted that each and every ground feature that needs to be reconstructed must be covered by at least 3 images taken from different position and orientation. Probably taken more, but at least 3 is needed. And the SFM techniques is less sensitive to color resolution of the images, so the position and the orientation of the camera is not a matter of concern, though there are some cautions. I'll talk about that later. Next. Yeah, so this is the flowchart. They at first the flowchart of the paper. So at first they set up the flume sediment filling and the pier fixing, then the bed level, and then they capture photos and send them to for the image processing, and they start the run, flow the water, and after the run they stop the run, and then again they capture photos, again they pre-process, and after the run, they also take the observed data by the gauge and the sensors, and by image processing, they SFM and all that, they get the morphological variation of the first DM and second DM of, I mean, before the experiment and after the experiment DMs, and then they check the accuracy, and this is the evaluation of the flow of the paper. Next. Yeah, so a little bit of SFMDM. Here they used the Agisoft photoscan software. Since the photoscan software SFM uses SFM principle and also takes the advantage of latest multi-view 3D technology, SFM component detects feature matching common points in all photographs which are stable under viewpoints and match them. Then it generates descriptor for each point from its local neighborhood to detect more correspondence across photos, and based on these are based on shift algorithm. Okay, next please. Oh, and the SFM here, they create sparse 3D points. And next please. Yeah. So the custom algorithm is used to identify conjugated the features between images and create the 3D sparse point clouds. And this 3D by greedy algorithm approximate the 3D sparse point clouds, we change them to 3D dense point clouds, and by meshing them we get 3D surface, and from this 3D surface we get the texture map of the generated texture map of the photo, and as a result the DEM is generated, which can be exported by specifying required special resolution parameters. But here's a thing to note that the for the photoscan software is expensive. We to minimize the cost, we can download some packages and execute different step of SPM, SFM, MBS technique for generating high resolution DM. Okay, next, please. Okay, so these are the result. The left one are three circular scour hole, and the right ones are three hexagonal scour hole. Here, as you can see, the black points are the scour holes, and uh, the in the below in the below side there is some color map for elevation. As you can see, the the more we move from the get away from the scour hole, more the the more it is the elevated, but after but the flow, when the flow direction, for the flow direction, uh, where the from where the flow started, their elevation is higher than the later part. These images. Okay, so next. Okay, for accuracy assessment, they have used RMSE, root mean square error, and MAD, mean absolute deviation. For the data, they the elevation prediction from predicted elevation in DM and the observed data by Gauge and this. Okay, so the error analysis proves that the predicted DM elevation for each run is adequate to represent complex bed surface morphology. And they also said that the accuracy could be better if the ultrasonic sensor had high precision, but whatever we get from the sensors or gauges, we take them as our original data. So if they have high precision, then we get the more original data and the accuracy would be more better. Okay, but still the accuracy of in this process what we get is much more is better always, and reliable for morphological analysis. Okay, next. Yeah, these are the R2 score for the hexagonal pairs. As you can see, H2 fits the regression best here, but the slope is slightly greater than 1, and the y-intercept is negative, as you can see, as it's shown in the figure. And for H1, i- this is for H1, this is over predicted. As you can see that the red line is the linear fit of checkpoints, and checkpoints are the blue points. So as you can see that H1 is over predicted, but H2 and H3 are under predicted. Next. Okay, there are some cautions in this flow, that we can't use blurred image, as they have removed it immediately when they captures any because it can cause the mismatching of conjugated points. And there's also a degree of orientation constant, which should be maintained up to 10 degree for better accuracy. uh, and convergent images can be used along with parallel images in order to mitigate the nonlinear dome effect in the DM. Yeah. Next, please. Okay, so for the conclusion, as you can see that in the paper they have used circular pairs and hexagonal pairs. So it thus closed range photogrammetry can be used in any shape of pairs, and the accuracy achieved in DEMs are in the scale of millimeter to submillimeter. So therefore, it can be concluded that SFM technique can be used to collect high resolution data studying morphological changes. We can use it for high resolution data. And the SFM technique is easy to implement and cost effective, efficient than the classical photogrammetry techniques. So we can use it even it is useful in a laboratory setup or any kind of. And then next, thank you. Thank you, ma'am. Thank you. That's it from our side.
Yes.
We're open to questions.
Yes. Thanks, Arnab. Yeah, so this was a nice talk. Also, this was different from the other talks in the sense that it showed a very different photogrammetric side of the application of computer vision. And one of the things to note is that, whenever you deal with uh, analysis from satellite or drone imagery, it is this kind of pipeline that you will see. So it was nice to see an example of this pipeline. There could have been many terms that you did not know or did not understand, namely, for example, DEM, which is digital elevation map, these kind of things. But if you sort of gloss over those for now and try to just accept the gist of this, which is the sort of pipeline that they described, and how that pipeline can be enhanced using CNN. So that was the point, I think. And the other point that is to be highlighted from this talk, also from Shioli's talk, some more is that when if you end up doing computer vision in the industry setup, then there is no getting away from the fact that you will have to. This is true for other data analysts also, but mostly for very true for computer vision, that you have to get yourself acquainted with the domain of where the problem is coming from. So if you're working with satellite or drone imagery, you will have to at some point understand what are ground control points, bundle adjustment, and DEMs, and how to use the GIS software, for example. In real life computer vision problems, you do need to get acquainted with the domain much better. Then, it's not just you run a CNN and you're done. So that's not how it works. So, yeah, so these are the two highlights from this talk that I would like to mention. Does anybody in the audience have a question or a comment? Okay, so if there are no questions, then let's meet again at 2:30 for the last talk in this series of presentations. Okay, thank you, Taher, Sumeet, and Arnab.
Thank you, ma'am.
Talk was
Thank you,
very
ma'am.
interesting.
Thank you all.